So I'd like to introduce Professor Mario Guarracino of the University of Cassino in southern Lazio, and he'll be talking about graph embedding.
So, thank you so much, Pierre. I'm very happy to be here, and as you can imagine, I am a little bit, still have a little bit of jet lag. I hope this will not affect my presentation. So, and today we have two parts about, and I will talk about graph embedding. So I will start from the very basics. I know that many of you might know this, but still we have also some people online. I think it's a good thing to do to start from the very basics. So. Okay, so what is a network? We are at a complex network workshop, so let me introduce. A network is just a collection of points that are somehow joined together by some lines. So the points are joined because of the context, depending on the context. So the points are usually called vertices, nodes, actors, and so forth. And lines are edges. And there are, of course, many real problems that can be modeled as networks. And individual parts are linked in some way. For example, internet is a network, as we know, and human societies can be represented using networks. So why should we use networks? First of all, because it is an universal language for describing complex data. So we can model a very complex problem using networks. And they come, as I said, in many different, from many different sources. So we have networks that come from science, technology. I will do some examples very soon. And they also have a shared vocabulary. So it is something that we, of course, we like because we can use the same wording, let's say, the same notations in many different areas like computer science, social science, and so forth. And also, given that there is a lot of data that is available, there is this avalanche of data that is available, we can actually build networks. We can build networks. Starting from this available data. And the impact of networks is known. There are so many applications, and we can better understand, have more insights in many different applications. So what happens is that when we model a problem using networks, we can model the entities, the individual components, but also their interactions. And this is not always the case if we use different ways to model our problem. And on the other hand, it is in some applications it might be interesting in analyzing the pattern of connections that exist between or among those components. And because those patterns might heavily affect the performance of the underlying model that we are trying to model, the underlying problem that we are trying to model. So, for example, in social networks, the patterns that are present affect the way in which people obtain information, they form their opinions, and so forth. So, analyzing this very complex model gives us much more information than analyzing raw data. And for example, if we analyze patterns in network of financially connected companies, might provide evidence of some causal behavior among financial assets. So we might understand more. There are some very beautiful papers that have been published on this topic. Sergei Butenko, Valery Kalyagin, Panos Pardalos are among those that introduced the first representation of economic and financial entities using networks. So, very simple example, what is a social network is a network of people. We might have some people, so each point represents a person, and then we have a connection. Here there is also a direction. Maybe this person liked the post of this other person. There are also some people that like their own posts, so there are some structures like this. And we know that there are some people that receive more likes than others. So looking at the structure of this, we can understand a little bit more. This is, of course, the same if we look at Twitter or any other social network that is available, that is actually available. And the studies at the beginning of social networks were based on very small scale networks, whereas we know that nowadays a social network can have billions of people that are connected. So we have structures, networks that are composed of billions of nodes that are connected by a large number of connections. And another example of a network is, for example, the co-authorship for statisticians. So this is, it's not a very new paper, but still is a very good example just to show. For example, we can say that each of those nodes is a person, so is an author of some paper, and two statisticians are connected if they wrote a paper together. And the more paper they wrote, the thicker is the connection that it exists. And on the node is bigger, the size of the node depends on the number of papers that this person authored. And we can also color, so somehow we can find actually we have some communities of people studying different parts of statistics. Okay, so we can look at this and we can have an idea of what is happening inside this network. This is a very rough approximation because we know, for example, that a paper is not authored only by two persons. Usually it can be authored by 3, 4, or more. So every time that we want to model this condition, we need to create a click inside the network. So maybe an hypergraph would be a better representation of this. And there is also another missing variable that is time. No, there is no time. This is a temporal graph, is something that changes over time, but we are just looking at a snapshot of it, and we are trying to understand a little bit more about this. So it might be interesting in finding some communities, so understanding how people that study, for example, economic statistics interact with people that study social statistics and so forth. So we can try to apply some algorithms to have a better understanding of what is happening in this network. Another example is, of course, the internet. This is a very interesting project that tries to highlight the breadth of internet. So somehow this is a study that is devoted to the fact that people want to understand if the backbones, these different colors are different countries in different continents, and they want to understand if the bandwidth is enough or not. So they try to picture out, they try to picture the whole internet and to understand where are the bottlenecks. So this is also very important and very interesting problem. So, but also in molecular biology, there are so many examples. For example, protein-protein interactions. We know that very different organisms can have a very similar genetic code, but they are very different. For example, a tomato and a human being maybe share 90% of their DNA, but of course we wouldn't say that we look like a tomato, or maybe someone else, not me. But still, no, we don't look like tomatoes, and this is due to the fact that more complex systems, living beings are more complex because the interactions among proteins are more complex. So proteins aggregate in pairs or in pairs to perform more complex tasks. And there are many different types of networks. For example, metabolic reactions can be modeled. The stoichiometric equations, the description of the metabolism can be described at its steady state using a network, and there are many other things that we can do in biology. And let's make a small joke. So we look at this object in which we have individuals, and two individuals are connected by a friendship, and they say, oh, look, this looks like a social network. And then we have another situation in which we have some proteins that are connected because they interact to perform some complex tasks. And they say, oh, look, this looks like a protein-protein network. And then we have in chemistry, for example, we have carbon atoms interacting on sigma electron bonds, and again, it looks exactly the same. So as a mathematician, what we say is, oh, you see, they look all the same, let's call it a graph. So, as Poincaré was saying, mathematics is the art of giving the same name to different things. And I would add, sometimes this name is a little bit strange, why not call it network, right? So this is somehow, those two terms, graphs and networks, in some communities are exactly overlapping. In some other communities, there are some little differences. In some cases, for example, networks in which the nodes have no label are called graphs. So it pretty much depends. But for the rest of this talk, of this tutorial, I will just use them as two synonyms of the same concept. So, the formal definition: a network is a pair, is an ordered tuple of two sets, the set of vertices, the nodes, and the set of edges, the existing connections between the nodes. I'm sorry. One of the pen, okay, of the order. Then those connections can be traveled in both ways, undirected networks, or we can only travel in one direction. This is the case of directed networks. We might have directed acyclic graphs that are situations in which we cannot, starting from one node, we cannot go back to itself following a path inside the network. Then we have cyclic graphs. This can be either undirected or directed. So in this case, we can go back from each node. We can follow a path that brings us back to the same node. And then we have weighted. So weighted can be a number, can be a qualitative variable. It can be anything. And we can weight both the nodes, as in the case of the statisticians network, coauthor network. We can sometimes weight nodes, sometimes weight edges. They can be positive, negative, whatever. Sometimes we can weight both. And when we have a loop, like in the case of the social, when we have a node connected with itself, we call it loops, as in the case of the social network. Last but not least, we have multigraphs that are graphs in which we have multiple edges. So this also takes different names depending on the context, on the community, and sometimes there are also graphs in which we have different objects that are coexisting in the same network. So different type of nodes, like in bipartite graphs, or different types of connections, like in the case, sometimes they are called multigraph, or they have some other notation. So there are many ways, many simple ways to represent graphs. The first that comes to mind is to take a matrix that has as many rows and as many columns, a square matrix with as many rows and as many columns as the number of nodes, and we put a 1 in row I, column j, if node I and node j are connected. So in this case of those 5 vertices, we have exactly this representation. This sometimes is helpful, sometimes is a little bit heavy. We know that in many networks the connections are very sparse. So using all this space to store 0 is not always convenient. This is somehow a quite old statistics that says that Facebook network has only 2 billion users. We know that they are much more than that, so this is a little bit outdated, but still we are talking about very huge networks. So, and okay, and so as I was saying, in some cases when the situation is very sparse or we have in mind some particular applications, we might decide to use some other representation. For example, the edge list, in which we just list the edges that are existing, or the adjacency list. The adjacency list says that vertex number 1 is directly connected with 2 and 3, and so forth. So the first has the limit that if a node is present but not connected, it will not appear in this edge list. The second, whereas the second is a little bit redundant, because if the network is undirected, 1 is connected with 2, 2 is connected with 1, naturally, and we are storing twice this information, so it might be a little bit heavy from the point of view of the memory footprint. Nevertheless, depending also on what we want to do, so which is the algorithm that we want to apply, one data structure might be better than another. So, and depending on what we would like to do. So, what are the standard machine learning tasks, statistical learning tasks that we can do on networks? Well, we can do node classification, node regression. So all the standard, let's say, data analytics tasks can be brought to networks. So, and we can also try to predict, for example, if a link will appear between two nodes. Or we can try to do community detection, so to find communities of nodes that somehow are similar to each other, and also we can also see network similarities, for example, comparing two networks, how similar or how different two networks or two subnetworks are. So, so the first example is node classification. Suppose that we have a graph in which we have a certain number of nodes belonging either to class yellow or to class green. Suppose that we have some other nodes that do not have a label, and we want to infer we want to predict the node label. So we want to predict if this is a yellow or green node. This might be, for example, a group of people that are friends on a social network. Some people are Android fans, some other people are Apple fans, and we want, and for some others we don't know, and we want to infer which if they are Apple fans or Android fans. So another example is of node classification is the classification of protein functions and protein functions. Biologists are a very well organized community. They have ontologies, and they use, for example, one ontology that is called gene ontology, in which way they describe in a formal way which is the function and the process that is associated to each gene. Some of the genes code for proteins, so we might be interested in knowing the function of some of the proteins, of some of those genes products, which is the functions of the others. So this is again a problem in classification. Another problem, as I was mentioning, is the link prediction. So if I want to predict if the appearance of some links, will those two people become friends on Facebook? Will this person put a like on this post on Facebook or whatever? So what we try to do is to make a predictions on the appearance of links. Okay, so this is another example about mafia meetings. So this network represents two families of mafia members. I'm Italian, so this is the best example I could make. Those two is Mistretta and Batanesi, and those two mafia families somehow are connected and do business together. So in this representation, in this network, we represent people. So the red and the yellow circled points refer to the bosses. So these are the big guys, the padrino of the situation, and there is a connection if they have they have an association, so they are doing something bad together. And there are those white nodes that are subjects that are close to those mafia association or somehow useful for their purposes. And in this case, the width of the edge represents the number of meetings that those people had. There are other networks like this. There is a famous network, the 9/11 terrorist network, in which there was somehow a very similar representation. And there are different tasks that you can try to do to predict if there is a link, if two persons will appear, so will meet, or for example, to try to detect some grouping, or for example, finding critical nodes. So if there are, which is the minimum, for example, which is the minimum number of nodes that I should delete from the network in order to disaggregate the network in itself, so that the parts that remain connected are small, so small that they cannot harm in a very bad way the society. So, so what happens? How do we somehow how to behave? Which is the process, the life cycle when we apply machine learning, statistical learning to graphs? So the first thing, we start very often from raw data. This is not the only case. We might start from some analytical descriptions, like in case of metabolism that I was saying before. But still, let's say that we start so in general, in machine learning, what happens is that we start from some raw data, then we structure them, so we build tables, we go from data to information, and starting from this, we apply some machine learning method which produces a model. So we start from data, we go to information, and we arrive to knowledge, applying some algorithm. What happens so in this phase, what happens is that to go from raw data to structured data, we have a part that is called feature engineering. In some cases, it's easier. In some cases, this is very heavy. Imagine, for example, medical imaging. So going from the CT scan to some features that might describe each of those images is very difficult, very heavy, very demanding. In case of and these are the downstream prediction tasks. So what happens is that when we go to networks, somehow we automatically learn the features. So there is a slightly difference between machine learning and what happens on graphs. So what happens is that, so what does it mean to this feature learning for network, for graphs? Somehow we want to start from a network, we want to take a node, a vertex, and we want to associate to this a vector in a space, a d-dimensional space. So if we associate to each of those nodes a vector, then doing node classification becomes a supervised learning problem. It becomes a supervised classification problem, and everything becomes easy, right? So so what we will talk about today, it will be all related to how we get those vectors. How do we get those representations? Okay, so if we will look at the problem, firstly looking at the single nodes of the graph and of the network, and then we will try to understand if we can do this for multiple networks. So suppose that you have multiple networks, how do you embed, how do you obtain one vector for each graph, so that you can do, so in this case, the statistical unit, the observation becomes the graph in itself. So you can classify, cluster, or do regression on a set of networks. If I'm going too fast, please tell me. I was drinking a lot of coffee, trying to overcome my jet lag, so maybe I am a little bit accelerating. Why is it hard? So this morning we were generally talking about deep learning. We had a very beautiful introduction to some very specific machinery that somehow use deep learning. And when we go to deep learning like convolutional neural networks, somehow they work on grids. So it's a very specific structured type of data. And the same we can say, for example, for text or sequences. When we go to graphs, this is not true anymore. And so we have to overcome these limitations. So in general, networks are complex objects. And therefore, the topological structure, the wiring of those networks needs to be taken into account. So we don't have anymore something that is very well structured. There is no fixed ordering or reference point. No, this sentence comes first, this sentence comes later. We don't have anything like this. So, and of course, there is also the problem of dynamicity. So we can have graphs that change over time. These are usually called temporal graphs, but this is out of the scope of this talk. So let's go to the traditional approaches. Okay, so how did people, because of course this problem, now people have been working on this problem for many years. So let's see what were the first, let's see which were the first solutions to this. So the traditional approaches were somehow using traditional data analytics, machine learning. We can call it in many ways because this is a moving target. No? An algorithm, this morning we were talking about SVM, support vector machines. So support vector machines, the first paper that I remember was by Olvi Mangasarian, no? That was a mathematician. But if we think, many computer scientists think that there is something that is in machine learning, right? Support vector machines is in all books about machine learning. So it looks like more related to computer science, but support vector machines is also something for statisticians. No? In the end, Vapnik published it in 1995 in the Nature of Statistical Learning Theory. That is the first time in which we have the exact formulation of support vector machines as we know it now. So sometimes the over definition is not useful. So, but in general, this to say, we will call it machine learning. Let's use this notation, but still, we can change it without loss of generality. These are somehow okay. So traditional approaches, what they do? They try to represent networks using some features, some statistics from the network. So you take the network, you compute some statistics, many of them, maybe 20, and you have a vector of 20 features. So now, for each node, let's say, you take each node, you compute 20 statistics, you have a vector of 20 numbers. And you say, okay, I got this vector that will be useful for the downstream task. And this was, of course, the first thing that was tried. So, for example, we can take the degree, the number of edges that each node has. So, and we can. So, if we take the adjacency matrix, we just see how many nodes are directly connected with node U. We sum on the rows, and so on the columns. So in this case, this is a very simple statistics. Of course, very different. Of course, this is something that is describing the nodes, but not very specifically. So if I take all the edges, all the edge counts for all the nodes of a graph, this might represent many different graphs. So many different graphs might have exactly the same degree for each node. So this is not unique. So this is a not unique representation. Of course, we don't like it. We don't like it very much. But still, this is very useful because it says somehow how each node is connected with its neighbors. So it gives a description of what is happening inside the node. So. Then another measure. So another measure that we could use is node centrality. So how central is a node inside a network? Of course, the degree, the edge degree is also a measure of centrality, right? Because if a node is very in the periphery, maybe has only one connection, one edge, connecting with the rest of the network. But here what we want to know is not only how central is the node in itself, but also how central are the neighbors of this node. Okay, so we want to have a more extended vision. So we want to understand the centrality of a node with respect to the centrality of its neighbors. So this is obtained. This is in case of eigenvector centrality. We define it via this recurrence relation in which the node centrality. I'm sorry. The node centrality is connected with the node centrality of the neighbors of the node. So if we can rewrite this very simply, and what we end up is an eigenvalue problem. Okay, so the eigenvector of the adjacency matrix that is related to the largest eigenvalue will give us the values for the centrality for all the nodes in the network. So this is another statistic that we might use. Or we can use, for example, the clustering coefficients. There are many definitions. In this case, what we are counting the number of edges that exists in a neighborhood of the node U, divided by the total number of pairs that are present in the same neighborhood. So the maximum number of edges that might be present among those nodes that are in a neighborhood of a node. So this is another different way. So, but there are so many that of course it's impossible to describe them all. This is just to have a way to go a little bit in more detail. So this clustering coefficient, as I was mentioning, somehow says how tightly are clustered is the neighborhood of a node. So how many edges are existing between the neighbors of the neighbors of a node, and a clustering coefficient equal to 1. This means that all the neighbors are neighbors of each other, so they form a clique. And there are different ways to represent this centrality, and there are many different ways to actually define this clustering coefficient. And what is interesting to note that the real world networks have higher coefficients that one would expect if the nodes were sampled at random. So this is the example of the person that wants to have an envelope delivered to another person, and we know that somebody proved that in only 5 or 6 steps, so giving this envelope to a friend and this friend gives to another friend, can actually reach whatever are 2 persons on the Earth, they can reach each other in 5 or 6 steps. Okay, so this was, as I said, these were the first somehow attempts to try to model the nodes using some vectors, using some statistics that I was saying. Then there were some other studies. These are more recent. You can find a very beautiful description in this book. And so somehow those node embeddings again encode nodes using some vectors in a low dimensional, let's say, in some vector space, and they somehow summarize the structure of the node neighborhood. So somehow they try, from the point of view of the node, they try to describe what is happening in the surrounding. So the structure of the local graph neighborhoods. So what we do, we can say we project those nodes in a latent space, trying to maintain some characteristics of the nodes. So if 2 nodes are close, in some sense, we want that in this embedding space, the representations are close. That is more or less what we were, this is not different from what we saw this morning. You know, when we were representing sentences or words by vectors, we wanted that words that had the same meaning in a context, of course, because we can only talk in that context, and also similar representations. Okay. And okay, so those node embeddings in general are explained in terms of encoding and decoding graph. So what happens here in this encoding decoder model, the encoder maps each node in a vector that is called the embedding, and the decoder takes this node representation and tries to reconstruct what is happening in the neighborhood of the node in the original graph. So the context in this case is the graph, and we try to understand what is happening around it. So, this encoding is a function that maps the set of vectors in Rd. So we will call those vector embeddings with ZV, one for each node one for each vertex in the graph. And historically, the first methods were those shallow embeddings. So these shallow embeddings means that somehow in computing those vectors, we are not somehow sharing any parameters in the construction of the embeddings. And in this approach, it's if we want the encoding of a node, we just go in the matrix that contains one vector for each row, and we go to the right row, and we take the embedding of this. And so Z is the matrix. It has as many rows as the number of vertices, as many columns as the dimension of the space in which I am embedding. And okay, this is it. So the encoder can be generalized, and we will see it slightly because it's a very long, it's a very huge literature in this field, so it's very difficult to collect it in in 2-3 hours. So I will just give some references, and maybe if you are interested, we can get in touch and go further on this topic. So as I was mentioning, so this idea of encoding can go beyond this shallow embedding. So somehow the encoder can also use some features that are related to the node, and also some information that comes from the neighborhood to compute this embedding, those vectors that represent. And these are called graph neural networks. So the decoder now, what does it do? It takes the representation in case of pairwise decoders, that is the most common case, we take pairs of nodes, and the decoder function somehow assigns, taking the two representation of the nodes, assign a value. And these decoders somehow are used to predict the relationship, the similarity that exists between pairs of nodes. So, for example, a simple decoder might predict if two nodes are neighbors in the graph. So suppose that we have a pair of embeddings, so we have those two vectors that we have somehow computed using the encoder function. We will go through this also in a minute. So we take ZU and ZV, and the goal is somehow to optimize the encoder and the decoder, so that we want to minimize this reconstruction loss. So what we do, we take the decoder of the two encoding. So we take the two vectors that represent the two nodes. We compute this real value that somehow tells us how similar, how close or how distant are those nodes, and we want this to be somehow close. So this matrix, we want to be close to some matrix S that contains the similarity measures between the nodes. For example, the similarity matrix might be the adjacency matrix. Okay, so in this case, what we are going to do is to try to minimize, to try to get a decoder encoder and the decoder such that the vectors that encode the nodes are such that this quantity is minimized. So the decoding of the encoded nodes of those two vectors is as close as possible to this similarity matrix. So this is the loss function, the general loss function. So now everything is about understanding what type of loss function we want to use, what type of encoding we want to use, and on different choices we left different algorithms. So this loss function measures how far are the estimated distance between the encoding of two vectors and the true values of this similarity existing among those vectors. And depending on, as I said, on the decoder and S, we can have many different algorithms. So in particular, for example, if we use as a decoder the L2 norm, the L2 squared norm of the difference, and we use a general similarity measure and a loss function like this, we end up, I will briefly introduce this method later, then we end up in what is called the Laplacian eigenmaps. If we take the scalar product between these and we use the adjacency matrix as a similarity matrix and the L2 norm, the squared L2 norm of the difference between the decoder and the similarity, then we end up in the graph factorization, and we have many others. So the last two, we will talk also about those, because somehow in this case we are introducing something that is some probability, let's say. So we have another little bit of information to try to obtain those encoding. So one way to view these encoders and decoders is we can look it as a matrix factorization, and because somehow when we decode the local neighbor structure from the node embeddings is like trying to retrostruct the adjacency matrix. So from this perspective, from this point of view, this can be addressed as a matrix factorization problem. And okay, this is what I have already said. So we might one of the earliest factorization-based approach is called the Laplacian eigenmaps, and this is somehow built on spectral clustering. And in this approach, as I was mentioning before, the decoder is based on the L2 distance between the two vectors that are representing the nodes U and V, and the loss function is somehow weights the nodes accordingly to the similarity existing in the graph. There is a beautiful tutorial by von Luxemburg that was written many years before that all this was invented, but in which you will find a very beautiful description of the spectral clustering, and in a way also of the concepts that are beyond these Laplacian eigenmaps. So what we are doing, we are somehow penalizing the model when two nodes that are similar with respect to this similarity matrix that we are using have embeddings that are far. And if S is chosen to be the Laplacian matrix of the graph, then the embeddings that minimize the loss functions are the solution for the spectral clustering, which means that if we want to project embed in a d-dimensional space, what we are taking are the smallest, those embedding vectors are the d smallest eigenvalue of the Laplacian. Okay. So another one that I was describing, was another method in which we were using as a decoding function the scalar product between the two vectors. Okay, so we assume that the two nodes, the similarity between two nodes is proportional to the dot product of the embedding. And we have different ways in which this is implemented. We have this method that is called graph factorization, graph rep, and hope, depending on the other choices that I was mentioning before. As we see, this bibliography is somehow starts in 2005, 2006, but the big bunch, the many methods were developed, let's say, in the last maybe 10 years, no more than this. So in this, those last three methods somehow combine this inner product of the two vectors representing the node using this square error, and they differ on the way in which they define the similarity existing among the nodes. So they implement different strategies. Of course, there is no free lunch theorem. So there is no single method that can solve all the problems. So depending on the problem, we will choose either one algorithm or the other. Okay. So, so far we have been introducing those methods that somehow introduce that only use some deterministic measure of the node similarity and dissimilarity. Node similarity, and this very often we end up in an S that is somehow some polynomial function of the adjacency matrix, and the embeddings, those vectors, those representation in the latent space are optimized so that the scalar product of UV is equal to S of UV. So we can try to use some stochastic measures of a neighborhood, and this gives us rise to other methods. So, for example, this is the case of deep walk and node to vec, because those two methods, they both use a shallow embedding approach as an inner product decoder, and the thing is, the difference is on how they compute this node similarity. So instead of reconstructing directly the adjacency matrix A, they try to optimize the embeddings using using random walks. So somehow the goal is to learn an embedding so that this quantity that we call PG of T of U and V, that is the probability of visiting of a random walker starting at the node U, which is the probability of a random walker starting from node U to reach node V in exactly T steps, with a shortest path of length T. And usually T is a small number, because otherwise this becomes very heavy computation. And the key difference, again, is that this similarity measure is stochastic and asymmetric. Yeah. You fix T is transposed. No. Ah, yes, sorry. This is, yes. Yeah, you need to learn it. Yeah, it's fixed. But how you fix, you need, you fix it in the sense that you choose, and but which is the actual value that you use, you need some strategy to understand. So you learn, okay? It's a fixed, but it's not fixed in advance. It might change a little bit. You never go very far, because then there are some other consequences in having very large explorations of the graph. Okay, I will talk about this in a moment. So the key difference, as I was saying, is that now we have some form of stochasticity. So if we want to train this random walk embedding, the general strategy is to minimize the cross entropy. So D is the training set on which we train our, this is the training set of random walks that is generated by sampling random walks from each node. This is also, there are different works that address this specific topic of sampling each node, but this would require 3 more hours to explain. So, for example, we can assume that that the n pairs of co-occurring nodes from each node U are sampled from this distribution. Yeah. So, so node vec is another slightly different approach on the same topic, and this employs a node contrastive approach. And somehow we take sigma as the logistic function, and we try to minimize this loss function, where gamma again is an hyperparameter that we need to learn. Okay, so somehow what are the limits of these? What are the limits of those methods? The limits of this shallow embedding is that somehow there are no parameters that are shared between the nodes and the encoder. So this is somehow a limit for this. And because if we might share some parameters, we might improve the efficiency of learning. And also this might provide a way to regularize the problem that is often useful. And from the computational point of view, the number of parameters grows linearly with the number of vertices. So this might, so shallow embedding might be impossible to use on very large datasets. Those days, there are very large datasets that are used for as a test bed. For example, there is this Open Graph benchmark that is a large collection of different graph datasets for different graph tasks: node classification, graph classification, edge predictions. And as far as I remember, for graph classification, we have a number of graphs in the order of millions, I would say, but it's very, very large. You can just go in the, it's open, and you can, and there is also a leaderboard in which people try to how do you say, to compete to each other to get the best possible results. So as I said, shallow embedding is not suitable for a massive graph. And the second thing is that we have been talking about the network in terms of its topology and its wiring, but we never talked about the possibility to use some features that are related to the nodes. So somehow in this construction, the fact that a node might have some features never came into play. There is also another limit, that is transductivity. So in general terms, we have 2 types of algorithms: those that are inductive and those that are transductive. Transductive algorithms are those that in which you cannot add a new node, you cannot add a new graph. So you get a representation of your dataset, and that is, okay? If a new observation arrives, you don't have a simple way to take this new graph, for example, and represent it in the space, in the embedding space. In inductive algorithms are those for which we can do inference. So we can, for example, given a new unseen observation, we can, for example, classify it or whatever. And in nature, the methods that I've been describing so far are transductive. So they are very good in characterizing what is happening around, but they are not good in case the new observations arrive in adding them in this embedding. So how can we solve this problem? We will discover in the next half of our talk, and we will talk about these graph neural networks. And I will be very general again because the time is limited. And but we have 1 hour. How long did I talk? 1 hour. At 2:30 we have a coffee break. No, at 3. So maybe I can go a little bit further, so the next part will be, sorry, I got confused. My jet lag is hitting me hard. So yeah, let's go a little bit further on this discussion, and because somehow I have 2 more things that I wanted to describe. One is those graph neural network models that is interesting in my opinion, and then I have this part on full graph embedding. So how do I take a family of graphs and I embed in a space for further analysis? So I will go a little bit further on this. Sorry, I was promising a break, but it's not the case. And do you have any question or answers? Because sometimes answers are better than questions. So, yeah, it depends. Depending on the technique, of course, if I have a directed network, if I have a weighted network, you can always generalize. And of course, you need to generalize the method that are beyond. So if you are using shortest path, let's say, to describe this similarity somehow of the nodes, then you need to generalize shortest path to the weighted. That is not very difficult to the weighted. Yeah, that is the representation. So it's the vector that represents the vertex. Yeah. Yeah, but somehow this vector represents the node. Okay, the fact that the graph is directed represents the edges exist. So somehow the similarity, let's say, in some cases, in some of the algorithms that I was describing. So yes, it's always possible to generalize. Not all methods can be generalized. So depending, as I said, there are multiple algorithms because there is no free lunch theorem. There is no single algorithm that can address all problems and solve them all. I hope if you have a more technical question, then we sit and we write. Oh, sorry, I'm going forward. Close your eyes, I am spoiling the rest. Okay, exactly. Yeah. So somehow, as I said, this is a probability. So, and this is somehow, so I have a random walker. This means I have somebody that is sitting in the node and can choose any edge at random to progress. So one step is chosen at random. So I ask myself, which is the probability of reaching in a certain number of steps, starting from one node to another node. So now if there is a direction on the edge or there is a weight, of course, not all the edges are possible. Yes. Yeah, but this is, we were talking, Yeah, for example, if we were using, now I understand, if we were using the scalar product to represent the distance, let's say, of two vectors, then in that case, that is symmetric, yes. Yeah, yeah. Yeah, yeah. So, okay, maybe we can go back to this. So not all methods are applicable to every problem. Many methods are generalizable. You need one moment, yeah, you need to think about it and to find a solution to this. Okay, in some cases you can, in some cases you can't. Okay. Okay, so, yes, please. Mm. So, so the question, I repeat for those at home, is when we compute this probability based on shortest paths, we always fix the distance of those, the sides of this of the ops of the shortest path. So, but this might be, in case of a very large graph, might be inhibiting the fact that I can explore larger portions of the graph. Did I understand? Is growing, yeah. So it might be extremely local. So there are different things that come to my mind. The first thing is from an application point of view, we know that the diameter of many graphs in real cases is very small. So in this case, this is not a big deal. Okay, so this is the first thing that comes to my mind. The second thing that comes to my mind is the fact that if you explore too much, if you go too further, what might happen is that you get the same representation for all the nodes. Because somehow, if you go too far, in the end, in the exploration, all the nodes will look more or less the same. I will explain this a little bit in more detail later in this discussion. So it might be a disadvantage to go too far, Maybe, but again, so graph neural, so again, it is always possible to find some small adjustment, so to somehow increment the number of shallow embedding methods that we have. In some cases it will work, in some other cases no. So it will solve some specific problem like the one that you were mentioning, or I have a graph in which the diameter is very high, I want to explore in more depth, starting from each node. In some other cases, maybe the existing solutions, fixing t equal to 2, 3, 10 is very big, it will be more than enough. Okay, so it will be, it's still, I think that it requires some understanding of the techniques and some knowledge of the problem in order to understand which method, which parameters, and also, of course, you need to learn. So somehow you need to experiment to get the right parameters. I hope this answers your questions. Okay. So transductivity, graph neural network. Okay. So as I was mentioning, I'm repeating what I've been saying so far. So somehow these shallow approaches that we have been discussing so far somehow are optimizing this vector. And in the next that we are going to discuss are graph neural networks which is a framework for defining deep neural networks on graph data. So the key idea is to generate a representation of the nodes that depend on the structure on the nodes, but also on some feature information that we might have on the graphene itself, on the nodes of the graphene itself. So as I was mentioning at the very beginning, the standard machinery, the standard tools that we have in deep learning do not apply to graphs. So we need to rethink our methodologies in order to take into account the complexity of the network, of the object that we are trying to represent. And in case of a convolutional, for example, as I was also mentioning, I was putting a picture at the very beginning, CNN are well defined if you have a grid structured point. And so we need somehow to define a new type of deep learning architecture in order to address this type of problems. So this one idea could be just to start from the adjacency matrix and to input it to a deep learning network, because in the end that is a very well structured object. But what happens for example, we could generate the embedding of the entire graph simply flattening, as we do using neural networks, for example, in the case of images in which we flatten the representation of the object that we want to represent, and we can feed it, for example, to a multi-layer perceptron. And so A of I will be one row of the adjacency matrix, and this symbol is the vector concatenation. The problem here is that this approach depends on how we are ordering the nodes. So if we change the ordering, everything will change. And of course, we don't want this. And somehow, sorry. So indeed, what it means is that the model that I was showing is not permutation invariant. And this is something that we always want, is actually that it is a permutation invariant. We don't want different results if we change the numbering of the nodes. And somehow we want a function, so we say that a function f, let me define this, is in permutation invariant if f of PAPT transpose is equal to f of A, where P is a permutation matrix. And we say that is a permutation equivariant, sorry, if this is a proper, so if the result is a proper permutation of f of A. And permutation invariance means, as I said, that this function f does not depend on the ordering that I have on the rows and columns, on the indexing of my nodes. And equivariance means that when it changes, that the output of f is permuted, but I can recover these permutations. And Shallow encoders are permutation equivariant function. Actually, there is a deeper motivation for which we want this type of characteristics, but for the moment we will just leave it on one side. And this is always a key challenge when we are learning over graphs. What we can, so when we define the graph neural networks, somehow we need to define what is called the neural message passing, which means how we take into account nodes that are nearby in our computation, and we will focus on this message passing network in itself, and we will also try to see how we can use a set of features that are available for each node. So now we are introducing another little piece that is each node as a feature vector. So we can associate to each node a certain number of characteristics that might be, of course, interesting. Also, in a social media, I might describe each individual using the time that he stays on the network, the number of posts, the number of likes, and the connection that he or she has with the other people in the network. So I am adding more features to describe the problem. I can provide a representation to an object that is more complex than before. So in this message passing, so during this message passing iteration, we have this HUK that corresponds to each node U according to the information that is aggregated by some neighborhoods. So we have this aggregation in which we take a node, we take its neighbors, for example, B as neighbors A and C. We take into account the information that it comes from them, we aggregate, and so forth. So, for example, let's make I will do an example in a second. So, what happens is that somehow we are computing this representation HU at step k plus 1 with an update operation, and this update operation consists of aggregating some information that belong to the nodes that are in a neighborhood of the node that I am considering, and then using this aggregated information, I will update the representation that I have of my node. So two operations, update and aggregate. Now this aggregate is usually represented, I'm sorry for the small circle, but I couldn't make them large. PowerPoint sometimes can be very tricky. And so we, in general, what we do, we represent this operation, so aggregating information in a neighborhood using this notation, M and U, that is the neighborhood that I'm exploring at step k. So this M and UK is the message that is aggregated from the neighborhood of, what does it mean? So most simply, it can be, for example, I can sum, I can average all the information, all those feature vectors of the nodes that are around in my neighborhood. So this update function then combines this message that comes from the other nodes and with what I have with the previous embedding of the node that I got at step k minus 1. I was sure that there was an example. Okay, it will come later. So let's say that we start at when k is equal to 0. As we said, each node U has a vector of features, some vector. So I start assigning at k, when k is equal to 0, the vector, so HU is equal to XU, the set of features that I have initially for each node. And after running k iterations of this GNN, what I end up is the embedding for each node. So I get my vector ZU that is exactly HU at step capital K. And since the aggregate function takes sets as input, then we can conclude that this is a permutation invariant. So if I change the numbering, this will not change anything because I'm considering a neighborhood of a node. So as I said, we need a starting point. So we need a vector consisting of some features related to the node. But what happens if I don't have? So if I am in the previous, in the very beginning, in the case at the very beginning, then there are some tricks that I can use. For example, I can actually provide the statistics that we were mentioning at the beginning, the node degree, the centrality index, the clustering index, and so forth, to each node. And we start from that, and we can start this iterative process. Another popular approach is somehow to use identity features, so somehow the numbering of the nodes. So we provide a one-not indicator feature, so a vector in which there is only one in one position that identifies the nodes, and we starting from that to feed our graph neural network. So yeah, but if you don't have anything, what would you do? It's just one of the possible solutions. Maybe computing some local statistics, some node statistics might be a better option. I agree. So at each iteration, what happens? So I start with this feature vector, suppose that I have. At the first iteration, k equal to 1, all the node embedding vectors will contain information from this neighborhood, from the nodes that are at distance 1. At the second iteration, all the node embeddings will contain the information that has been aggregated at the previous step, so it will contain the information that comes from the nodes that are at most at distance 2. And so after k iteration, we are aggregating information that come from a k-hoop neighborhood, okay? So, what type of information are we encoding? From the nodes? So in a way, we have two types of information. That is, one is the structural information, the fact that we are exploring a neighborhood. So we are actually taking into account which are the nodes that are directly connected or in k-hoop connected with a node. And then we are also taking into account the information that comes, as I said, from the features that describe each node. And this, in some applications, might be very effective. So this is the second part that I was showing, this feature-based information, the fact that I have a vector describing each node. And after k iterations, the embedding will encode this information that comes from a neighborhood that are at a distance of at most k from the node in itself. And this is not different from what happens for example, in CNN. So rather than acquiring information from some patches, local patches of the image, in this case, we are aggregating information of a local neighborhood. So we are extending this concept from a very well-structured object to networks, graphs that are not structured in the same way. So actually, what we have been discussing so far is somehow abstract. Now we do some examples, so I will show some of the algorithms and how they handle those ingredients to build up the GNN, the graph neural network. And in general, we have seen that we have two functions. And if we give some concrete instantiations of these update and aggregate functions, we will get very different models. So we can rewrite this message passing. So how I get this representation at step k of the vertex u using this matrix notation. This is convenient because somehow we are expressing as a matrix vector product. So this is, from a certain point of view, efficient. It is not efficient, for example, if the graph is very large, because I would need to store a very large data, So what we have here, what we say is that at step k, the representation that we have of edge u is a sigma, that is a nonlinear function of this linear combination. So this is a matrix vector product in which of the representation at step k minus 1 and of node u and plus this message that we got. You remember we were aggregating in a neighborhood of the vector. And what we get is that we need those two matrices that we need to train. Okay, so these are two objects that we need to train. We will not go into the detail of training. This morning we had some discussion of how important is the training and how difficult is the training of those. The transformer use some matrices that are pre-trained, and only some countries have the power, the computational power, and the money to train those objects. But here, in a very general sense, what we have is this linear combination. There is also this term that is called the bias term that in general does not always show up, but somehow it has a regularization effect. But I will not go into the detail of this. So, how can we define our GNN? So the message that I receive is from a neighbor, is from the neighborhood of node U. I just sum all the representation. Maybe I use some normalization factor because it might happen that I have very different values in the HV that are of the nodes that are in a neighborhood of U, and then I update. So this is the message passing, and I update the representation, the current representation, using this message, using this sigma, this nonlinear, this function sigma of this linear combination. This is exactly the same, the figure that we saw before. So from a mathematical, from an algebraic point of view, this is very simple, matrix vector products. So everything that we don't need to think about it more than much more than this. On the other end, so this is a general description, and we can and we defined what are the basic operation of the GNN. And we can rewrite, as I was mentioning, this model as a matrix of node representation, where A is a graph adjacency matrix. Okay, let me see. I want to stop at some point. Okay, let's make a no. Yeah.
Or this can go around forever. So depending on where I stop, the number of iterations of my embedding, I end up with
Yeah.
just there is some property that is okay.
So it will depend on the characteristics of those metrics, right? Yeah. So in general, since this come from the data, so you cannot say in advance. But the real breakthrough in neural networks has come when people understood that they didn't need to take this process forever, but just few steps would provide representations that were very useful for their tasks. Yeah. Yeah. Yeah, of course it will not. Yeah. No. Yeah, yeah. So it will depend on the case that you have at hand, but very few iterations will just do the work. Yeah, as we said, the number of hops that you take is always very small. Also because, and we will see this in the next, when you go too far from the node, the representation that you get, those representation, each representation of each node becomes more or less all the same. So there is an over-smoothing phenomena. So you don't want to go too far because otherwise you don't see the characteristics anymore. There was a similar question this morning related to the BERT. There was something that was very, 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 very similar. So because you want to distinguish things that are similar from things that are different, right? So what you want to do is to try to get representations that are somehow describing how close two nodes are in a graph. So I think that this is, if there are no more questions, I think that this is a very good moment to have a rest, and we will meet again in 35 minutes, right? So let me help to do the math, at 3:30. Okay, thank you.